Morning, Shelby. Hi, Naya. Can you hear me okay? Can you hear me, ladies? Hear you fine. Sounds good. How about the screen? Can you see the screen okay? I'll put up some of the text. So I'll give everyone a few more minutes to get in. Thank you for answering on the chat. How's everybody doing? I figured there'd be a little bit of a lag. Make this chat bar a little bigger here. There we go. Oop. Of course it disappeared. Here we go. Let's see, it's paused. So it looks like a good bit of you are here. Like the name, by the way, Xavier. So I'm going to see how this goes today, and then I'll see if you guys prefer doing this live, or if you would prefer if I just recorded it and put it up. I think it's best if you can ask questions directly. So chat's here all the time. If you have a question about anything I'm doing, you're having trouble hearing me, seeing something, put it up there. I know there's a delay. And I have the chat up on my screen here so I can see if you guys are responding. So everybody ready to get started? I think we're still missing a few people, but I'm assuming some of those people are going to wake up eventually, or maybe decide to check their email. So the first thing I would like to do is just do a few problems from the exam that you guys just did. I started grading them. I have not finished. Morning, Shanice. I was a little unsure if you guys were comfortable with differentiation, so I wanted to redo these problems, and then I think I'm going to give you maybe a couple extra quizzes of just taking derivatives that you guys can work on to earn some more credit. They're not going to be directly added to the test, but they will be, be more possible points in the course, which will make it easier for you. So I just wanted to do these real quick for you. Let's see if you can see this green first. And I know there's a giant glare in the middle of the board. That looks like that's too light. Yeah, I can't even see that. Let me just use black.
I am Iron Man.
Oh, lovely phone. Let's see, it was log 5. Plus e to the 1/3 over pi was the one problem that I gave you. And so that problem there, if you were to differentiate, all of those things are constants. And so the derivative of this thing is just 0. And I apologize for the screen focusing on me as I walk in and out. I'll try to get out of the way so you can read it. So I saw a lot of different stuff there, like 1/5 for natural log 5, and I saw people differentiating the e over pi and making it 0 over 0. None of that stuff is good. Another one I wanted to do for you real quick was we had x cubed cosine of pi x plus e to the x over 2 cosine of x. So I'm going to write this out fully first. This would be the derivative of x cubed times cosine plus, leave x cubed alone, take the derivative of cosine of pi plus take the derivative of e to the x over 2, leave the cosine, plus leave e to the x over 2, take the derivative of cosine. So then I just need to differentiate all those pieces. Some of the things I saw were you would differentiate all of one problem, right? So all of x cubed cosine pi x, and then add it to this. Or I saw things like derivative of this times derivative of that. I don't know, some combination of this times that one. So it's just a double product with some chain rule thrown in. So this first one here would be 3x squared cosine pi x. Then we would get a minus pi x cubed cosine, sine x, or pi x. Then, and that's because of the chain rule, where you get a pi from inside here, and then the cosine becomes minus sine. Then derivative of e to the x over 2, that is 1/2 e to the x over 2. Leave the cosine alone. And then finally, derivative of cosine, which is going to give us minus sine. So any questions about those two problems before we start this next section? Yeah, that's basically the end result. There's not anything in common of all four of the pieces, so there's nothing you can take out. It's ugly, but that's all. That's it. I may do number 3 for you later, the one that was 1 over sine minus sine all over cosine. There's a real easy trick to it, but I want to get through some. Oh, I ask you, would you like me to do that problem before we begin the new stuff, or go ahead and start the new stuff? Alright, so first off, e to the x over 2 for this problem. We can write that like this. I can call this thing y, for instance. Then let u equal x over 2. Then the chain rule right? dy du times du dx. This here becomes e to the u. And so derivative of y with respect to u is e to the u, or e to the x over 2. And the derivative of u with respect to x, if you'd rather, you could write it that way. That's just some constant times x. And so that's just a 1/2 out in front. So that's how I get 1/2 e to the x over 2. I saw someone said they would like to see number 3, so I'll just go ahead and do it. I think we're going to have a little bit more time. Hopefully we'll finish early, we'll see, because I can't really stop and let you guys work on the board. So I'm hoping that you get some time to maybe go over these on your own. If you have some suggestions, feel free. But I think I'm just going to go ahead and work the problems for you. Am I okay to erase this? I think you've all seen it now. And I'm trying to, I'm recording. I'm hoping I can put this up so that you guys can go back and watch it if you need. I'm sure you'd never want to do that. So while I'm setting up this problem, how do you guys like the setup? I got a dry erase board, I got my projector sending the problems to the board. Let me see if I might be able to grab a book or two and stuff it under the camera, see if that helps a little bit. Alright, so bear with me here. Looks like that's already a little better, right? Yeah, I know there is a glare from the projector. Looks like it's just raising it up now. See if we can tilt this guy down just slightly. You say perfect, but I can still see a giant glare, so I'll just take your word for it. So I see you say something about screenshots. You're welcome to, you could always do a print screen, and you're welcome to use Blackboard to talk with your fellow students. So I think that might be a little clearer, so let's go ahead and do this problem. I can see my ugly mug there. Alright, so my approach to this problem was to try to simplify it first, right, because it's ugly. The 1 over sine, nobody likes it. It's not going to be fun. So what I did was first I factored out a 1 over sine. That then would leave behind a 1 here, and if I try to take a divide by sign here, well, that would really make this thing a sine squared. And if you don't like that, then just go ahead and multiply it back in and you'd get the same result. And this is now all over cosine. Then we should recognize that 1 minus sine squared is cosine squared. So then we can go ahead and cancel the one of the cosines in the numerator with one in the denominator. And we are left with cosine over sine, which is also the same thing as cotangent. Haven't done any calculus yet, I just simplified. So at this point I could just take the derivative of cotan. Which is minus cosecant squared. So that was the way I approached it. I like to give the problem because, you know, it takes a little bit of thought to get to that point. You could have certainly done it using quotient rule. It's just a little more simplification, and you got to be really careful about taking the derivative of 1 over sine. The derivative of 1 over sine, you could either change it to what that'd be, cosecant at the beginning, or you could treat it as its own quotient, or you could do it as a chain rule, right? You could make that sine to the minus 1 power and do it that way. Right? If I said 1 over sine, let's just understand the 1 minus sine squared. So the step here to go from here to here, I factored out a 1 over sine. So if you're not comfortable with it, multiply it in to make sure it's the same thing. All right, so you would get 1 over sine, and then sine over, or sine squared over sine is just another sine. So if I wanted to rewrite this guy, let me not write it that way. I could make it that, sine to the minus 1. And then when I differentiate, you bring the minus 1 down, make it to the minus 2, and then derivative of the inside, which would be cosine. So this would turn out to be cosine over sine squared would be the derivative of that guy. That's another way you could approach it. All right, so I saw someone ask if I could do the problem with x's and y's, so the implicit differentiation. So I guess I'll go ahead and go through that one quickly, and then we'll go ahead and start the new stuff. I think it's good you guys have had a week off. It doesn't hurt to do some review. If it does, you got to tell me through chat. I can't hear you. I'm sure it's hurting being up this early after having a week off. Oof. This eraser's terrible. Get the wipe. Whoa. All right, that's a little better. All right, so let me go ahead and do that problem. So we had x squared plus y squared squared, and that. Excuse me. So implicit differentiation, remember we've got to take the derivative of everything, and then whenever we have a y, we put dy dx. So, excuse me. I'm going to do the right-hand side first because it's much easier. So, taking the derivative here. This is going to be 2x minus 2y dy dx. Just bring the 2 down for each one, and because this is a y, I get a dy dx out of it. So there's already one dy dx that I've got to isolate with this other one that I'm going to get. Actually, let me write this over here. There's not enough space there. So I need to differentiate this. So I'm going to forget what's inside, bring this 2 down. So I get 2 times whatever's in there. Then I need to take care of the inside, which is 2x plus 2y dy dx, which is almost the exact same thing as over here, just a plus sign instead of a minus sign. So I've got to get the dy dx's together. To do that, I've got to get this out of these parentheses. So I've got to somehow multiply all this stuff out, right? So the first thing I decided to do was, this 2 might be a problem, so I'm going to go ahead and stuff it in here. Or even at this point, actually, I notice everything over here has a 2. And this 2 is multiplied by everything over here. So if I were to cancel the 2's, we could do that. So now, the way I approached this was, instead of foiling this whole thing out, I distributed. So I said, this is going to be 2x times the entire set of parentheses there, plus this times that entire set of parentheses. So this is 2x times this plus 2y dy dx times x squared plus y squared. Now I did that because I need to get this by itself, so it doesn't do me a whole lot of good to distribute. and get it, then I'd have it inside of 3 terms. There's no need for that. I could just do it this way. And then over here, I have that. So now I just need to get these 2 terms together. So I will move this one over here, move that over there. So this is that now. And then the last couple steps, I need to factor out my dy dx. So this is, now I'm going to go ahead and multiply this in. So this will be 2x squared y plus, actually, hold on. No, I'm not going to do that. It's a bad choice. Bad choice. Always try to factor if possible. Both terms have a y in them. So I'm going to factor out a y dy dx. If I take that out here, I am left with 2 times these quantities. Oops. Almost forgot. If I take out a y dy dx out of this, I get a plus 1. And then over here, again, both terms have an x. Factor that out. Take an x out of an x, you leave a 1. Multiply this 2 in here. These two result in something quite similar. And then you just solve for dy dx. So I think I'll need to do that over here. Got that, I'd be ecstatic. If you plug the numbers in right, that's pretty good too, but all the real hard math is right there. Please flood the chat with questions and or complaints, whatever comes first. This is the one with the graph. It wasn't the last one. Lost you a long time ago. Uh-oh. Did a lot of algebra. You are certainly welcome to multiply everything out. You could do that if you like. At the beginning of the problem, you could have went ahead and squared this as well. If you prefer to do that, it makes the derivatives easier. So feel free to try that one, or try it that way. Obviously, you have a question besides just that I lost you, feel free to ask. So if it's all right with you all, let's see. Yes, there was more than one part. It was just now plug in a point, so it's 0.5 and negative 0.34. But like I always joke, you know, if you can't plug some numbers in here, What do you mean by leave up the stream? So, to try and answer that, I am recording. I am hoping to leave them either on Twitch, or if you like, I could try to upload it to Blackboard. But certainly maybe take a screenshot now so you don't lose it, just in case. Where are we at? Why is it 2x minus 2y dy dx? Where are we at here? 2x I'm not seeing that part. This here maybe? Y is 2x minus 2y dy dx over 2x minus 2y? First step of the problem, yeah. This was the right-hand side of the equation. I had to flip them. Right, so this is the derivative of that. This is this derivative. And then this guy here is the chain rule. So if you would prefer, you could always FOIL this and differentiate the whole thing, and you would still get this result. It would just be expanded. Not quite sure if I answered your question there. Alright, so I'm going to go ahead and erase this, and I'm going to go ahead and start new stuff. Please feel free to ask questions. If you want to keep it, like I said, this is my first time doing it, so if you want to take a screenshot quickly, you can do that. Oh, eraser. Great, I'm going to have to go out into the coronavirus just to get an eraser. That's terrible. Nice. So you guys can't see, but my cat is just standing over here, staring at me right now. Alright. So originally, I was planning on doing the applications of derivatives for today. And so that involves a couple theorems. Let me just scroll back up here. So the first one is the closed interval method. And before we do any of these theorems, the very first thing is critical numbers. So a critical number occurs at two positions for a graph. When the derivative is 0, so here it says f prime of some c, that c is our critical number. So if the derivative is 0, you can get a critical value, or critical number, I'll say critical value often. Or if the derivative does not exist. So basically what this is saying is we're often going to have some kind of fractional value, and in those cases you would set the numerator to 0 and set the denominator to 0. It's basically all these two things are saying. So this is numerator equals 0. This one is denominator equals 0. All right, so closed interval method tells us that we can find what's called an absolute min or max as long as the function is continuous over some interval AB. And sorry, cat distracted me. To do this, we have the critical values that we have to find first. Then it says to evaluate the function at the critical values and at the endpoints, A and B. And whatever the largest number you get out of that is your max, and the smallest one is your min. So it's pretty straightforward. We just have to take a derivative, set it to 0, solve, plug those numbers in, see what you get. So in case you're wondering, the whole reason for this, that we're trying to build to a point where we can graph a function with calculus, so without a calculator. And I know that sounds really dull to you all, but it is quite impressive to be able to do that without using the calculator whatsoever. So let me just get rid of these guys. All right, so this first one says use the closed interval method. So to do that, we have to take the derivative of this function. Pretty straightforward. Right, this is all just a polynomial. So g prime, that is what, 12x cubed, d48 x squared, and 36x. All right. I need to set this thing to 0 now, right? That's how I find my critical values. Everything there, I notice, has a 12 and an x in common, so I'm going to factor it out. So left behind there would be an x squared. Then this would be 4x and plus 3. X squared minus 4x plus 3, we're looking for two numbers that multiply to 3 and add to negative 4. So I always write this here, multiply to 3, add to negative 4. I think some combination of 3 and 1 will do that for us. If they are both negative, when multiplied we get a positive, and then they'd add to negative 4. So that looks good. So this is 12x, x minus 3, x minus 1. So that's going to give us three values for which x is 0. So I plug in x equals, or sorry, this is going to give me x equals 0, this one's going to give me x equal 3, and that one's going to give me x equal 1. So 0, 1, 3. These are my critical values. So you might be thinking, okay, well at the top you told us if we take the derivative, we got to set it to 0 for the numerator and the denominator. Well, we've only got a numerator here, right? So there is no undefined portion for any kind of polynomial, so that we don't have to worry about that, and these are our only critical values. So then the closed interval theorem says, go ahead and take those numbers, 0, 1, and 3, plug them into the original function. So I might actually see if I can get some help here from you guys. Can you plug 0 into this function? Well, I can do that one for you. That's easy. 0. Plug 1, 3, and then we also need to do the endpoints. And it's also important that you make sure that these numbers are within that range. So all three of these numbers are within that range. That's good. It means we use them all. So then we're going to do g of -1, and we also need g of 4. So if I could get you guys to plug these numbers in real quick to this original function for me, and then just plop the number there on the chat, that'd be great. Hopefully that's helping you stay awake. I think this one's going to be 5, right? Chat's looking real active over there. Even with virtual I guess you're hidden. You guys still don't want to plug in some numbers. So I'm going to go grab my calculator. Hopefully when I return, there's some numbers over there. Help me out. Would you believe it? I can't find my calculator. Okay, so yes, we are taking the derivative, setting it to 0. We got the numbers. We then take those numbers and the numbers given, and we are plugging them into the original equation. -27, thank you very much. Somebody said they got 0, or was it 0, I think? Was that for g of 0? $32. Thank you. It's alright, you're forgiven. Yes, absolutely, this packet is on Blackboard. That's where I got it from. This is, I don't know if you can see it up there. It doesn't appear so. It's Applications 1, packet number 10. somebody plug in -1 real quick? 37. Thank you. Okay. So, all that just to be able to do this. Which number is the biggest here? Well, quite clearly it would be 37. So this is my absolute max. Which number is the smallest? Oddly enough, most people, or a lot of people, would say this, but it's really this guy, right? -27 is much smaller. So this is your absolute min. So what does that mean? What is it telling me? If I were to graph this function, not sure how quick Mathematica would load on my computer, so I'm just going to do a rough sketch. This is a fourth order polynomial, so it's going to look something like this. And then we're only going from -1 to 4. So let's say maybe that's here, I don't know. So it's saying that at 3, let's see, I guess we're going to need to go like that. Yeah, if 3 is the max, then the interval, then it's got to be going down at that point. So this would be 3, this would be 4. So here would be the, darn it. Let me just plot the darn thing before I do something silly. So hopefully my computer won't crash while I do so. Come on, mouse. Come back to this screen. Thank you. Do. All right. So I just need to quickly plot 3x to the 4th minus 16x cubed plus 18x squared. And I want to do this from -1 to 4. Okay, so if your numbers are correct, here's my plot. We said that the minimum occurs at 3. So here's 3, there's the minimum of the function, as long as we are restricting it from -1 to 4. Actually, in this case, it doesn't matter, that is the minimum. More importantly, the maximum says it occurs at -1. So that value there is larger than any value on the function from here to 4. Right? So if here's 4, I go over, -1's a little higher. So that is the max, that is the min. I better drag that back over if I can. Don't lose it. All right, where'd my chat up there? Good. Okay. Everybody good? I see some discrepancies in the values. I think we maybe got that figured out. Where's my mouse at? There we go. Okay. So I'm going to go ahead and try another one. See how that goes. And if you guys still have questions, please feel free to ask. I'll do my best to answer them. See if a paper towel works. Works just as good as the eraser did, I guess. I think I need to spend my off time inventing the perfect marker for these things. Didn't work too bad that time. Let me just scroll down here. Can everyone see those problems fine? Okay, good. All right, so now I've got to take the derivative here. Thank you for replying. So first thing, as I said, was take derivative. So h prime here. Now you might want to rewrite this as cosine of x squared, if that helps you recognize what it is you're differentiating. So this is a chain rule. I need to bring that 2 down in front. 2 cosine x times derivative of cosine, which is minus the sine. So overall, this is minus 2 sine cosine. Anybody recognize that formula? All right, so I'm assuming you may have your trig sheets. This is a common form for, let's see, what is it, sine squared, I believe? No, sine of 2. Sine of 2x. So 2 sine x cosine x is equivalent to saying sine of 2x. Good job, Anj. And then there's a minus there because I had my derivative, so I still keep that minus out there. So any questions about the derivative? I'll go ahead and post them up here. So I need to set this thing to 0. And I know you all just absolutely love trig functions. So how would I then find when that thing is 0? Well, first off, that negative doesn't matter, because I could divide by a negative. Then I could take the inverse sine of both sides of this equation. 2x equals the inverse sine of 0. And then finally, the x equals the inverse sine of 0 over 2. So my question then is, when does the inverse sine of, or what does the inverse sine of 0 equal? And that basically says, when does sine return 0? For what angles? So if we looked at our unit circle, right, sine is the y value. So it occurs here at 0, pi, 2 pi, and so on, right? However, right, so this has infinite solutions, right? This is 0 over 2, pi over 2, 2 pi over 2. So that gets us 0, pi over 2, and pi. Notice my bounds on the problem were originally 0 to pi. So I can't go any further. These then are my critical values or critical numbers. I need to take those and plug them back into the original function. So once again, I'm going to ask for your help. Can you plug 0 into cosine squared? Well, that one's easy. That's 0. I need, actually, I think all these are real easy. This is cosine squared pi over 2. Cosine of pi over 2 is 1. No, 0. I did this one wrong. This is 1. That's 0. There we go. Just slightly losing my mind. Okay, so we get 1, 0, 1 if we plug those in. So, what are my absolute max and what is my absolute min? Well, it turns out I've got two values that are the same here. Well, that's okay. It just turns out that I have an absolute max there and here, and an absolute min there. So just as a heads up, if I ask you this on an exam at some point, I would like you to say the point 0, 1 and the point pi 1 are the absolute max, and the point pi over 2, 0 is the absolute min. Alright, so I see someone asked, why did I multiply sine of 2x by sine of the minus 1? Okay. So if I want to solve this guy, the only way to get rid of a trig function like sine is to take its inverse function. So arc sine or inverse sine. And if I take that of both sides of the equation, that sine and inverse sine cancel one another, leaving me with just 2x. And then this side becomes inverse or arc sine of 0. You may not write that step often. It all depends, I guess, on if you took trig or if you remember trig, that sort of stuff. Or who taught you trig, if they taught you to do that. But that is the formal way of getting rid of the sine. So let me just go back over the problem one more time. We started with this function. I took its derivative. We set it to 0, solved for those values. With those values, we then plug them back into the original. Got our numbers here, and we look for the biggest numbers, that's our max, the smallest numbers are min, and it's okay to have more than one value as the max or min. So yes, I just answered that question. It's okay if you have more than one. I can't see what h equals. The original equation, you mean? H is equal to cosine squared of x. H of 0. Yeah, sorry, it's a little bit of a glare there, I suppose. Maybe I could... Nope, can't put it in the shadow. Sorry, H of 0 is equal to 1, and it is an absolute max. Can you see it up there? Yeah, for me, there's a glare right here, like a circle. Have you guys been seeing that the whole time? Yes, you are correct. It is 1, 0, 1. I mean, I could try lifting it up again. I know it's got to be a direct reflection back. I think it's always going to be there unless I was able to put this exactly perfect. I'll certainly work on that. I apologize. Maybe I'll put a little circle on the board here to try to keep me from going in that area. So yeah, h of 0 is 1, h of pi over 2 is 0, h of pi is 1, h of 0 and pi are the maxes, h of pi over 2 is the min. Any other questions? May I continue? While you guys are answering, I'm going to see if I can lift this up slightly more. Hey, it's still college. You can go do whatever you got to do. All right, I'm going to try and adjust this real quick. So again, bear with me. It doesn't look like that glare's reducing at all, does it? Looks like maybe I'd have to be above looking down. Ooh, that looks terrible. Maybe if I could get it way up there, we'd be all right. Technical difficulties. Still there. You'd think somebody that studied optics could figure this out, huh? I don't know if that helped at all. Doesn't really look like it. Can you all see okay still? That would get rid of the problem if I did it with paint, but it's a very strenuous thing to do. But that is an option that I might be able to try. Alright, so I'm going to go ahead and erase this guy. Another thing I can try and do is, if I have the resources and time, I can print these notes out and rewrite these and post them as well. I mean, I'd prefer not to do that because I don't want you guys to just print that out and then not actually get any discussion out of it. Alright, so we've got this guy, that one. What else we got here? Rolle's theorem. Okay. So I think I'm gonna skip that one for now and go to this guy. If we have time, we'll go back. If not, that'll give you some practice to try that one, and then you guys can email me pictures, whatever you need. If you like, we can maybe set up a Skype conference call type thing if you need to do that at some point. I know this is not exactly the ideal situation, but gotta try to make it work. Alright, so I wanted to do this one because I know for a fact that this is going to give us some something different than what we've seen so far. Plus this is a quotient, so we need to treat it that way. So let's find P prime. So I need low times the derivative of high minus high times the derivative of low. So I'm going to bring this 2 down in front. Leave this alone. Then I need to multiply by the derivative of the inside of this guy. So that's 2x as well. And then all of that over x squared plus 1 quantity squared. All right, so let's try and simplify. I've got x squared plus 1 quantity squared minus, this is going to give me 4x squared times x squared plus 1. Yeah, we do. You didn't see that? Must be that damn glare. Alright, so what did I say? This is 4x squared times x squared plus 1 all over. Computer glitch. Nice one. Stream got stuck. Alright, so that's slightly simplified. And then we can go a little bit further, because all three terms here have an x squared plus 1 in them. So if I were to factor that out, then I could cancel this with one of these. That then results in we got x squared minus 4x squared, that's minus 3x squared plus 1 all over x squared plus 1 cubed. That is p prime. As if that wasn't hard enough, we now need to find where this thing is 0, where this derivative is 0, and then we need to find when the denominator, right, is 0. That's when it's undefined. So I need to solve both minus 3x squared plus 1 equals 0, and I also need to solve x squared plus 1 cubed equals 0. So, let's see. Oop. Okay. I don't know who that is. If I move this to the other side, both quantities would be negative, or I can make them both positive. And then divide by 3 and take the square root. And as a technicality, I would get plus and minus there. And then this guy, it doesn't matter that it's cubed because it's equal to 0. If I take the cubed root of both sides, that's going to disappear, and so would the cube on that side. So really I just need x squared plus 1 is 0. And that gives us something interesting. Right, it gives us negative 1. So if I try to take the square root there, I get complex numbers. So it really turns out that this doesn't really give me anything. So then I need to plug my critical values, which are right here, and the endpoints back into the original equation. So I need, let's see if I can miss this glare here. Need your help once again. Can you plug negative 2? We need to plug in 2. We need to plug in square root of 1/3 and negative square root 1/3. I guess we can do these. It's 4 plus 1's 5, squared's 25. So that's what? 2 over 25, I guess. And then it's minus 2 over 25. I did that right. Please check me on those. Then plug in 1/3. That's going to be 4/3. So that'd be 1/3 over 16/9, or negative, you plug it in, it's just going to result in a, oh wait, that's a square root, not a whole number there. So let's see, plug in for -2, -2 squared is 4, plus 1 is 5, 5 squared, right? Okay. So I screwed this up. This is square root of 1/3 divided by 16/9. Like that. It's not exactly a nice number. Somebody go ahead and give me some decimals for these real quick. You got 27 over 100. Okay. So I'm pretty sure you got to plug in square root at the top, right? You guys can do it. Really, I just need to know if these numbers are bigger than those or not. Unfortunately, the one calculator I found doesn't have any batteries. It's a good excuse, right? Alright, you're going to force me to use my phone. Yeah, 0.324, that's what I got. Thank you. Yes, any imaginary number you would ignore. That's why these right here we didn't continue with. And then what is 0.08? Okay, so as a comparison, this is 0.08, and this was 0.3248 approximately. Of course, I wrote that right in the glare. Right down here. This one would be negative of that, as it should be. Okay. So these numbers are smaller, right? They're only 0.08. This here, then, these two are going to be our maxes and mins. So this is max, That's min. Any questions about that guy? My guess is if there are any questions, it's back here taking the derivative, but either way, I'd like to know. Alright, so I don't see anybody asking any questions. I don't know if maybe the chat's going a little slow or something else, but I'm going to go ahead and erase this guy and I can do Rolle's theorem and then I'll leave you be. Alright, so what is Rolle's theorem? Well, it says that if the function is continuous, which we should technically be proving all these, but I kind of let it slide a little bit, especially if we have a polynomial, that's always continuous, so we don't have to worry about it. Many of the functions we use are continuous. If you have a continuous function and it is differentiable. So what does it mean to be differentiable? Well, that is, by definition, the function has a derivative at x equals some value. Let's call it, I don't know, q. So by that I mean, you can take the derivative of the function and I plug a number in and it gives me something back that makes sense. I don't get undefined, I don't get 1 divided by infinity, I get back 5 or negative 1 million. I get something that's tangible. And the other part then says there has to be some values or the endpoints that f of a has to equal f of b. So we have to have all those things occur. It's got to be continuous, it's got to be differentiable, and the endpoints have to be equal. Then, somewhere along the line, somewhere between a and b, there had to be some constant c such that the derivative, right here at c, had to be 0. So let me just let that sink in for a second. And so this is a very simplistic graph, right? We could do something more complicated. Right? We could have something like this. And I could call this A and this B, right? Because they have to equal the same value for Y. So that says that I don't care what A and B are as long as the value of the function at A and the value of the function at B are the same. There had to be somewhere along the line that my derivative was 0. So let's take a look at this problem. So it says determine if the 3 conditions hold, and then find all the numbers that satisfy Rolle's theorem. So first off, we have to prove, is this thing continuous? Well, in order to prove that it's continuous, we have to talk about its domain. We're given the interval -2 to 4. What's the domain of this function? All right, what numbers am I allowed to plug in for x? Well, the domain of this function is -infinity to infinity. I'm allowed to plug anything in there. It doesn't matter. And then that says because this interval is in my domain, this function is continuous. So we can say continuous because -2, 4 falls between or in the domain. Then the question is, is it differentiable? So to make something differentiable, then we have to say, does this thing have a derivative? Well, obviously it does. Right, we could go ahead and find it. F prime is equal to 3x squared minus 4x minus 8. So that thing is differentiable. And then, we have a derivative. The question is, does the derivative exist along this interval? So once again, what is the domain of the derivative? So the domain here is once again -infinity to infinity. So we can say this thing is differentiable. The last thing we need to do is plug in the endpoints. If plugging in the endpoints into the original function gives us the same value, then we can find these numbers that satisfy the theorem. So I need to find f of -2 and f of 4. So f of -2. So that's going to be -8 minus 8 plus 16, that's 0. And if we plug in 4, it's going to be 64 minus 16 and 32. That's not what I do. This is 2 times this. There we go. Alright, so that's also 0. So both the endpoints give the same value in return. They both return 0. And so I can go ahead and find these numbers C that satisfy the theorem. Well, it says that there's some number C that makes the derivative 0. Okay, so take the derivative, which we found. 3x squared minus 4x minus 8. Set it to 0. So this one I think we might have to do by grouping. Let's see if it's possible. Multiply these two together, so 3 times -8. That's going to give us -24. So multiply to -24, add to -4. So can we think of two numbers that give us 24 to add to -4? I don't think that's going to work for us, is it? So So unfortunately, we're going to have to use the quadratic formula. So I need 4 plus or minus square root it's going to be 16, 4 times 3 times 8, all divided by 2 times 3. You guys with me? Am I boring you to death? Hanging in there? This isn't looking too good, right? Where did 16 come from? It's b squared here. Right, it's opposite of b plus or minus b squared minus 4ac. But now I'm looking at this and it looks like I'm going to get a complex number in here. So I don't think this problem's going to work out too nicely for us. Unless I'm doing something silly. Which is entirely possible at this point. My derivative looks good. I'm going to get 16 in common. That'll leave me with a 6 there, right? Get 4 out of that. That's 6. So 4 would come out. I'd have a negative 5 in there. I feel like I understood the previous ones, but this one is confusing. Well, that's because I made it confusing. I may have to just jump to the next one and come back to this one later and see why this number's not coming out nicely. The way I'm doing it right now, I'm getting an I, and I don't like that. Shouldn't be any I's involved. So I'm thinking I'm making a silly mistake here. So considering we only have about 12 minutes left to our normal class, let me jump to the next one and try it really fast. I'll come back to this one. I'll solve it and send it to you guys on Blackboard. I did something silly and I'm not seeing it right now, and I don't want to waste time, so let me just try another one, come back to that one. Let's see, we got cosine there, and we got mean value. Let's see if we can't do this guy here. Okay, so we got to prove it's continuous, differentiable, and that the endpoints are the same. So I'm going to tell you right now, cosine and then its derivative, which is going to have some form of sine in it, they are continuous, right? They go on forever. We can plug in negative infinity to infinity. So therefore, this guy right here is within those domains. So this is continuous. And it is differentiable. So it passes those. We then need to plug in the endpoints. So I need cosine of 4 times pi over 8. And then I need cosine of 4 times 3 pi over 8. All right, I'm just plugging these in to that guy and proving that they're the same thing. So I'm going to get cosine of pi over 2, and this is cosine of 3 pi over 2. And cosine of pi over 2 is 0, and so is 3 pi over 2. So the two endpoints are the same. Rolle's theorem then says there's somewhere in between those 2 points that should give you the derivative is 0. So first find the derivative. So f prime, the derivative of cosine is minus sine, but it's got something besides x in there, so take the derivative of that. That gives you a 4 out in front. So you get minus 4 sine 4x, and set that to 0 now, because I want to know where's the derivative 0, just like before. I would divide by negative 4. Now I'm looking for a place where the sine of 4x is 0. So I'm going to need to take the inverse sine again of both sides. I think I'm just outside the glare there. So these would cancel, and I would get 4x is equal to inverse sine of 0, or x equals inverse sine of 0 divided by 4. So inverse sine is 0. So where does the sine give us 0? Well, that occurs at 0 and pi and 2 pi and so forth. So this is 0 over 4, pi over 4, 2 pi over 4, 3 pi over 4, and you can do this all day, except we need to be between pi over 8 and 3 pi over 8. So 0 doesn't work. Let's see, 2 pi over 4, that's going to reduce to pi over 2. So the question is, do any of these fall in between there? So pi over 8 is half of pi over 4. So pi over 4 would fall in there. Pi over 2 is bigger than 3 pi over 8. So it looks like the only one that falls in between there is pi over 4. So again, the point of the problem was to find, is the thing continuous differentiable? That's real easy to state. Most of the cases that'll you can just kind of throw that to the wayside. Then you really just need to prove the endpoints are the same value. So just plug the numbers in, get zeros or whatever you get out of those. In this case, it was 0. And then finally go back and take the derivative and set it to 0, just like we were doing for the other case. But this time we're looking for numbers. Right, this is still a critical value, but we're looking for one that specifically says that it's between this interval. That's the only real difference here, besides the continuous and differentiable part. So any questions about that guy? All right. So I'm going to really quickly talk about the next one. I'm not going to do a problem. I want to leave the last few minutes. I would like you guys to give me any feedback from today, things that I can improve. So go ahead and please sound off on that real quick. I'm just going to talk about this really quick. So the mean value theorem is an extension of Rolle's theorem. You still need to be continuous and differentiable. The only difference now is that f of a and f of b are not equal. However, there is some value of x, which we call c here, where the slope of the tangent line is the same as the slope between a and b. That is the purpose of the mean value theorem. So in this case, you're going to take the derivative and you're going to set it equal to the slope given by the points f of a and f of b and ab, right? So you're going to use that and set it equal to the derivative and solve for c. So this time you're not plugging in equal to 0, but instead setting it equal to the slope between the endpoints. So I'll start next time with that. So we've got 4 minutes left. Like I said, please feel free to say anything here in the chat quickly. Let me know if there's anything that you think I can improve on. Obviously the glare. I also want to run through the names that I saw, make sure I got everybody. So I had that Naya was here. I see she just responded. Shelby. Armando, Christina, James, we had Jameson, Shriyam, Nate and Nathan, Garrett, Xavier, Ruben, Anj, Mike, Devin, and Shanice. Did I forget anyone? Oh, hey, there's Jonathan. Anyone else? Alright, my server kept saying there was an error and caused me to have to refresh the page and wait for it to reconnect. Okay, so, yeah, like I said, I am recording. Hopefully I can post it up for you. That would be ideal. Probably wasn't just you, and I'm sure it's probably going to continue to be a problem considering how many people are home and using their internet right now. So before you all go, just let me say thank you for tuning in. I would like to be able to see your faces interact a little bit more in chat, but I'm glad you enjoyed it. I was trying to make it as seamless a transition as possible. So if there's anything you guys miss, my next class starts at 11:30. I do have to do some stuff for that class, but if you need, you can send me emails. We can set up a chat if you need on Skype or something if you want to talk about some of the stuff we just did. Homework or quiz, not yet. I will be sending you guys something soon. I think maybe how we're going to do that is I might send it out on Blackboard and then maybe say, you know, return this to me in 20 minutes or something like that. That way you can't go searching for it online or saying, hey brother, can you help me, that sort of thing. Not saying that you would do that, but Just gotta try to keep things as kosher as possible. So I'm glad you enjoyed class. Sorry you lost connection. I'm not sure what that nacho's for. Test grades. I will get them to you no later than the end of the week. I just started grading them over the weekend, and it was taking me a long time to get through some of the problems, and I kept getting frustrated by seeing them. But I'll get them back to you as soon as I can. And like I said, I'm going to try to give you a couple extra little quizzes here and there to increase the amount of points possible in the course, which will make it a little easier for you to recoup some points. Alright, so I'm going to go ahead and end the session. If you guys have any more questions, send them to me on Blackboard or email. And enjoy the rest of your day.